Okay, all you beautiful people, these things are called less apparent U substitutions, and that's because the plot thickens. They get a little more interesting. Hopefully you've honed your skills on U substitution to be ready to look at something where it is a little more complicated. Again, the selection of U doesn't change. What's a good U here? Of course, the dude under the radical is a prime candidate. In fact, the derivative of U is also pretty much in the integrand. The derivative of U would be negative dx, so we can solve for dx, which is what we actually have there, and call that thing negative du. So we have a u and a negative du in the integrand. The problem arises now, or becomes more interesting, depending on your perspective, because there's another x wandering around in the integrand, and we can't mess with two variables. So go to u, or keep it in x. You can't do u and x together. We've already developed this bridge, this connection, the relationship between u and x to be that u is 4 minus x. We can use that guy to solve our problem of this extra x floating around by solving for x. If u is 4 minus x, then x equals 4 minus u, right? So we could make that substitution here. X is 4 minus u. Thereby substituting at each piece, we've eliminated the variable x. So it becomes the indefinite integral of 4 minus u for the x, and then the square root of 4 minus x, which we called u, times the negative derivative of u. So let's clean this up a little bit. We can't yet find the antiderivative because it's a little bit too messy. I'm going to pull out the negative. Then we could write u as to the 1/2 power for the radical, and then write this business that it was x as 4 minus u and the derivative of u. Now, before we can find the antiderivative, we have to still clean it up further. We got rid of the radical, that's nice, but now we have this product situation. So in order to find the antiderivative of each piece, we have to distribute the u through, so that we can go term by term, add a power, and divide by that new exponent. So keep the negative out in front. We have u to the 1/2 times 4, that's easy, 4u to the 1/2, and then minus u to the 1/2 times u to the 1 is u to the 3/2 with respect to u. So now, finally, everybody's in u. We have one variable, we have term by term. Now we can apply the reverse power rule, if you will. This is the negative. Let's find the antiderivative of 4u to the 1/2. U goes up a power from 1/2 to 3/2, multiplied by the reciprocal 2/3, and remember there's still a 4 as the constant out there. Then minus u to the power 3/2 goes up 1, that's to 5/2, multiplied by the reciprocal 2/5. And we're almost done. We can clean up by distributing this negative through. I'd probably multiply the 4 and the 2 together to make an 8, and we can't call it quits until we have negative 8/3 u to the 3/2 plus 2/5 u to the 5/2. But the party isn't over until we return to our original variable. So remember, we knew what u is. We're going to take that bridge again. U was 4 minus x, and substitute 4 minus x for each instance of u, and keep the rest of the stuff the same. Negative 8/3, 4 minus x to the 3/2 plus 2/5, 4 minus x to the 5/2 plus some constant c for the general antiderivative of this function. Here's another similar example, because just one probably didn't cut the mustard. Made it about as clear as mud, I'm sure. So let's see this process one more time. Now we are messing with x plus 5 times x minus 5 to the 1/3. You could try to multiply these things out, but then you kind of get stuck in this term, like, geez, what do we do with the 1/3 power? It's not like that thing distributes, and we can't necessarily FOIL it. So we're kind of stuck opening this integrand up. So let's choose that thing, that ugly, complicated thing that is the roadblock to our solution, to be u, x minus 5. Then the derivative of this u is simply dx. We've transformed this to be u, and dx is exactly du. So at least something from this problem was easy. Now, however, we have x plus 5. And that's a problem because now our integrand is in terms of x's and u's. So we use the bridge that we created, the connection between x and u, to solve for x. If u is x minus 5, x is u plus 5. And we can substitute that right here for x. So x is u plus 5. That transforms the indefinite integral to be u plus 5 plus another 5, right? That 5 was from the integrand, times u, plain old regular, boring, straightforward u right there, to the 1/3. And dx is a simple exchange for du. So let's clean it up. The indefinite integral of u plus 5 plus 5, u plus 10, times u to the 1/2 du. And before we can find the antiderivative, we need to break it up term by term. Distribute u to the 1/2 times 10, u to the 1/2 times u. That gives us the indefinite integral. U to the 1/2 times u, that's u to the 1 plus 1/2, or 3/2, plus 10 times u to the 1/2 with respect to u. Now we can do term by term, reverse power rule. U to the 3/2 plus 1, 1 is 2 over 2, that's u to the 5/2, multiply by the reciprocal, 2/5, plus 10 times u to the 1/2 plus 1 is 3/2, times 2/3, multiply by the reciprocal. And before you close the door, return to the original variable, return to x. So each of these cases of u is an x, really, some expression of x to the 5/2 plus 20 thirds, something with x to the 3/2, and that something with x is the relationship we established in the beginning. U was x minus 5 in both cases, and plus some constant of integration for the general antiderivative of this function.